This one?
Yes, thank you. Okay, well, welcome everyone to today's technical webinar from FREEDM. My name is Ken Delaney, and I'm the Director of Industry and Innovation here at FREEDM. We are a power systems and power electronics research center located at North Carolina State University. Our research projects span renewable energy integration, electric vehicle technologies, control techniques, microgrids, applications of wide bandgap semiconductors, and traditional power systems analysis. We have extensive lab capabilities, including multiple simulation labs for HIL development, an electronic packaging lab, and a high bay lab for evaluating medium voltage applications up to 15 kV AC input. Together with our industry partners like ABB, Duke Energy, Facebook, and the New York Power Authority, we are leading the electrification revolution. Hopefully, everyone is familiar with Zoom by now. We have disabled audio and video for all attendees, and we ask that you use the chat feature to ask questions. Just hover your mouse over the Zoom window and the button should appear at the bottom. Click chat, type your question, and we'll answer as many as we can. Note that this webinar is being recorded and will eventually be posted to the YouTube channel for the Department of Electrical and Computer Engineering at NC State. And I will now turn the presentation over to our presenter, Dr. Yiyan Lee. Dr. Lee, the stage is yours.
Okay, thank you, Ken, for the introduction. So next, let's start our presentation today. So the topic of today's presentation is meta-learning-based distribution system load forecasting model selection framework. So basically, we focus on the load forecasting problem in the distribution system, and we are trying to use a machine learning concept, which is meta-learning, to solve this forecasting problem. So this is a brief introduction for myself. Currently, I'm a postdoc researcher at NC State FREEDM System Center, and I'm working with Dr. Ning Lu. So in case you have any follow-up questions after this webinar, so please feel free to send me emails or give me text for further discussion. And these are my personal website and our group website for your reference. So my research interest mainly included the distribution system situational awareness. So basically, what I'm trying to do is to, based on the limited measurement data from the distribution system, we try to understand what is going on in the distribution system and what will happen in the future. So more specifically, I have done some work in the load PV forecasting and the load profile analysis and the super resolution technique and the behind the meter resource disaggregation. So the super resolution part is pretty interesting and will be presented by one of our PhD students in the next webinar. So welcome to join that one either. And the second part is the modeling and the control of distributed energy resources. So for example, we will try to estimate the personalized user preference. So that means in the energy consumption part, different user may have different preferences. For example, for the HVAC system, some user prefer a higher temperature setting, while someone prefers a lower temperature setting. So I try to use machine learning to automatically estimate the user preference. So we believe that the personalized estimation of user preference is very important for the control of load profiles. For example, the demand response program. Only after we know the personalized preference of each user, we can achieve very accurate and effective demand response for the HVAC load. So this is a personal introduction of myself. So next is the outline of today's topic. So firstly is the introduction for the background and the motivation. Next, I will explain the key concept of our work, which is Metalearning. And the next is the case study part to show how it works and how many accuracy you can achieve. And then is the field implementation. We try to give some examples to show how this technique can be used in industry. And finally, we will give a summary of today's talk. So let's dive into the background and motivation part. Basically, this is a brief background introduction about what is load forecasting and why we need it, in case some attendees do not have a very solid background for this part. So basically, as we know, the power system is a real-time balanced system since the energy storage is still in the early stage. So what we need to do is to keep the balance between the supply side and the demand side. So that means, for example, we will need to adjust the power outputs in near real time to follow the power load. So we will adjust the power supply to follow the power load. So that means we need to not only know what is the power consumption right now, but we need to know it in the next few minutes or next few hours, so that we can adjust our generators in advance to keep the system balance. So in order to know the future demand, we will need, as I mentioned, like a ultra short-term load forecasting for the next few minutes, and the short-term load forecasting for the next few days. The day-ahead forecasting can be used for scheduled generators. And then we will even need to use mid-term load forecasting or long-term load forecasting for the next few months or even years, so that we can decide how many generators we need to build years ahead. So this is the planning problem. So currently the utilities, maybe I will use a better pointer to, let me see. This is too small. This should be better. Yeah, currently the utilities mainly focus on the system level load forecasting. For example, for a distribution system operator, he mainly cares about the balance of his own balancing area. So he will focus on the system level for load forecasting. But we believe that in the near future, only the system level load forecasting will not be enough, because in the distribution systems, the operation modes is becoming more and more flexible. For example, currently we are having more and more microgrid operating individually, which may not connected or may connected to the main system. And we also have some net zero energy buildings, which may generate like solar power by itself and consume the solar power by itself. So we call it a prosumer. So such individual building also needed to be operated to keep it in a good balance. So that means we will need the forecasting problem not only in the system level, but also in some sub-levels. For example, the microgrid level or the single building level, or for even a single residential user level. So in order to solve this problem, we propose our Metalearning based methodology. So this is the background introduction. So actually, as I mentioned, we will have different forecasting problems in different load level. So this figure is a more comprehensive demonstration to show the complexity of load forecasting problems in distributed systems. That means we not only have different forecasting load level, we also have different forecasting horizon. For example, hours ahead, days ahead. And we also have different load components. For example, sometimes we need to forecast for the industrial load, sometimes for commercial load, and sometimes for residential. So different types of load will have different characteristics. So this also makes the problem complex. And we also facing different measurement granularity. For example, some smart meter data are in 15 minutes, and some of them are in 30 minutes, and some of them are in 1 hour minutes. And we also have different data availability, meaning sometimes we have only the load data, but sometimes we will have weather data and some other data to support our forecasting. So in summary, our forecasting problem is pretty heterogeneous in distribution systems. We will have different data availability and a different forecasting requirement. So that means all of these different problems cannot be well solved by any single forecasting model, because each model has its expertise area. For example, one model can solve a certain amount of problems, but it cannot solve all the problems. So that is why we need to use the meta-learning to achieve the model selection. So that what we want to achieve is that for different problem, we find its best solution among the candidate solutions, so that the overall forecasting performance can be improved. So next slide is analogy explanation for the meta-learning concept. So this is an example to show the traditional supervised learning task. For example, this is an image classification problem. We have some cats images and dog images, and this is our training set. We need to train a classifier F1 so that we can distinguish between cats and dogs. So this is a classification problem, also a supervised learning problem. So similarly, in our load forecasting case, we will have the historical data to train the forecasting model F1. And then we will apply the trained model F1 to forecast the future, which is our testing set. So this is a traditional supervised learning problem. And I guess many of you is pretty familiar with this type of problem. And the meta-learning is more of a cross-task problem, meaning we have multiple different tasks. For example, we still have the cats and the dogs classification problem, and we have the classifier F1 to be trained. And meanwhile, we also have another classification task, which is a lion and a tiger classification. So in order to do this new classification, we will have a new classifier, which is F2, so that we can distinguish between lion and tiger. So now the problem is we have a new forecast classification problem, which is, hey, someone told me, hey, yeah, please do the classification to distinguish between the chicken and duck. And now if you ask me this question, I'm pretty confused because I haven't seen this problem before. So I don't know which classifier I should use to solve this problem. So then I will probably try exhaustively all the possible solutions to solve this problem to see which one has the best performance. But certainly this strategy is pretty time consuming and is not that smart. So what meta-learning tries to do is that it will try to learn something high-level knowledge from the task 1 and the task 2, so that it will try to tell me which model I should use to solve the new problem. So for example, if the meta-learning agent can tell me, hey, based on what I saw from the task 1 and the task 2, I think you should use the classifier F1 to solve the new problem. Okay, now things will be much easier. I can use the recommended classifier to solve the new problem, and probably it will work well. But of course, it also may not work well. So it's just a recommendation. So in the case study, we will show how the accuracy level it can achieve to recommend a good model. So similar concept in our load forecasting problem. So basically we have different load forecasting tasks here as shown, task 1 and task 2. You can see that we call them different tasks because they have different load level, load aggregation level, and a different periodic characteristics and shape characteristics. So you can see that I think the y-axis should be kilowatt. So this should be like a microgrid or feeder level load profile. You can see that it's pretty smooth. And this should be probably a building level or microgrid, small microgrid level load profile. It has a lower load aggregation level and pretty fluctuating. So these are different forecasting problems. We may need different forecasters to solve them. So similarly, now we have a new forecasting problem. We can see that such a load profile, we have never seen it in the task 1 or task 2 because it is pretty different, right? The load level is very low and it is fluctuating significantly. So I think you might guess this is a residential load. Yes, it is a residential load profile. So the Metalearning tries to solve that based on task 1 and 2, which forecasting model you should use to solve the residential forecasting problem. So this is the explanation for the Metalearning concept. So, but this is just a concept explanation to show the key idea of our work. But in order to implement this idea, we have developed a 3-stage Metalearning framework to solve this problem. So this is the technical flowchart of the whole process. But I will not explain this in too much detail because it is pretty time consuming. And actually we already have a journal publication for this work, which is published in Applied Energy. So if any of you are interested in technical details, so you can refer to our publication or we can discuss it later. But here I will only explain the key ideas of each layer. So basically the stage 1 is the base learning stage. In this stage, we will define a lot of different load forecasting problems. As I just showed in this picture, we have a lot of different tasks. And then for each of the forecasting tasks, we will try to find out which model is the best. So basically, this is a labeling process to find out the best forecasting model for each problem. So we will use exhaustively way to test all the candidate models for each problem and to find out the best one. So this time, as you can imagine, this step is pretty time consuming. And the second stage is the Metalearning stage. So based on the stage 1 results, we have each different task and have the best model for each task. We try to build the mapping function from tasks to their best forecasting models. So this is the Metalearning stage. And the third stage is the online application stage. So once the Metalearner F is built, when we have a new forecasting problem, we can use the Metalearner to give us the model recommendations. And then based on the recommendation model, we can use it to solve the new forecasting problem. So basically, this framework, the first stage is time consuming, but it can be done offline. So we don't need to worry about the real-time performance of the first stage. But for the second or third stage, it will be pretty fast after it is well trained. So we can use it to make online model recommendations to solve the upcoming new problem. So next, I will dive into each stage to give some examples and the simulation results to show how it works. So this is the first stage. So as I mentioned, this is a labeling process to find out the best model for each problem. So here we defined over 800 different load forecasting problems, ranging from building level up to feeder level. So here is the 5 dimensions to define a load forecasting problem, if you still can recall in the first page. So we have different aggregation level, we may or may not have weather features, and we have different historical data lengths, like 1 month, 6 months, and we have different forecasting requirement. For example, we need to forecast the next 4 hours or 24 hours or something else. And we also have different data granularity. So once you combine the 5 dimensions together, you can define a load forecasting problem. So for example, the highlight one, when you combine them together, you will have a building level residential load forecasting problem with no weather feature. And what you have is 1 month's historical data, and what you need to do is to forecast the next 24 hours with 50 minutes granularity. So in order to define this task, we get the field measurement data from Wilson Energy, Pecan Street, and some weather data from NOAA. So these are defined based on the real data set. And in order to solve this over 800 forecasting problem, we prepared 10 candidate models as an example. So including SRM model of different structure, and the LSTM model, SVR model, which is similar support vector regression, and a similar day model. So basically, why we select these 10 models among the thousands of possible models, we have several considerations. So firstly, this is just original research. So we just select a few models as an example to show how the framework works. So we cannot use exhaustively all the models. So, but in your implementation, you can certainly introduce more models to solve this problem. So this means this framework is pretty extendable. And for the ARIMA model, you can see that we introduced 6 different structures. The reason we do this is to see that if our Metalearning framework can select the correct or the optimal model structure directly. So this is why we an explanation for why we selected these candidate models. So this is just a basic test case setup for the whole work. And the next is an illustration about how to find the best performed model for each load forecasting problem. So we are using the virtual forecasting, meaning we are using historical data to train each model, and we will forecast the historical data. We assume that this part of historical data, we do not know it, and we will see if our model can give a good performance on the testing set. So in this way, we can find the best performance model for each forecasting problem. So this figure shows as the number of virtual forecasting increases, our best model distribution tended to be stabilized. So for example, in this case, as our virtual forecasting increases from 0 to 60, our best model stabilized at number 9 model, which is the support vector regression model. So we will label this support vector regression model as the best model for this particular forecasting task. And this, after we find out the best model for all the problems, actually we cannot, you can see, we not only can find the best one, actually we can give a full ranking for the 10 candidate models. So this shows the whole ranking results for all the 800 problems. So basically, and a different color, you can see that the darkest color here, it represents the top 1 model for each problem, and the light color represents the worst model for each problem. So you can see that the top 3 model performance is pretty close to each other. So meaning for each load forecasting problem, we may have several available solutions. But for the low ranking models, for example, the top 9 model, top 10 model, in many forecasting problems, it will have a large forecasting error. So this means the model selection is pretty necessary, because once you select a low ranking model, you will have a very bad forecasting performance. So especially you can see that in this area, the difference of good model and a bad model is very significant. But in this area, the difference is relatively smaller. So here, the y-axis I need to explain, it is called the SER ratio, which is an error ratio defined by ourselves. Basically, its physical meaning is pretty clear. It just measures the ratio of our selected model to the actual best model. So you can imagine that once we select the best model, this ratio will become 1. But once we select a bad model, because the error of the selected model will be larger than the best model, so this ratio will be larger than 1. So this is a visualization of the over 800 load forecasting problems labeled by its best performance models. So this figure basically is visualized by the TSNE dimension reduction technique. So this is a statistical method that can reduce a high dimension problem to a low dimension problem. So in our case, we reduce it to 2 dimensions. So we can plot out such a 2-dimension figure. So in this figure, each dot represents a forecasting problem. And the different color represents its best models. So for example, this blue dot, it is one of the 800 load forecasting problems, and its best model is similar day model. So you can see that some tasks are pretty similar to each other, and they formulate clusters. For example, this is one cluster, cluster 2, and this is the cluster 4. And each cluster has a relatively more effective forecasting model. So you can see that in cluster 2, the LSTM model takes about over 30% to be the best model in this cluster. But definitely, there is no cluster that can be dominated by any single forecasting model. So this again shows the necessity of model selection. So, and this table shows some statistics about the results. So you can see that these 10 numbers just represent the representation of the 10 forecasting model. And the model number 7, which I believe is the LSTM, is the most selected model to be the best. So that means if you don't know which use, you can select the LSTM. It statistically has the best chance to be the best model. So, and we also give the time cost of each different models. So basically the LSTM model is deep learning model, so it is pretty time consuming in model training. And we also give the mean absolute person error and the SER error ratio for each models. So these are averaged values for each model. So this is the results of stage 1. So again, we define the different forecasting problem, and we find out their best performed models. So these are called metadata and will be used in the second stage. So in the second stage, we will try to construct the mapping from load forecasting task to their best performance models. So in order to do this, we firstly define some features to describe different forecasting problem. For example, we defined some descriptive features like data length, how many historical data you have, how many weather features you got, and what is the data granularity, something like this. So after this, we also defined some statistical features. So like what is the mean value, maximum, and the minimum value for each forecasting problem. So this is so for each, after we define this feature set, for each forecasting problem, we can have his own feature set. So from the output side, we will have we already know the best model for each forecasting problem. So this is a typical classification problem. So here we will use multiple classification algorithms and then combine them together by a voting mechanism to improve the accuracy. So this is because we believe a single classifier may have some wrong recommendations. So once we combine the different classifiers, so we can enhance the robustness and accuracy of the classification. So this is basically the idea of ensemble learning. So this is an example to show the scoring voting mechanism for the model recommendation. So basically, here, as I mentioned, we have, for example, a forecasting task number 1, and we already calculate its features like this. So it means for example, the first one is I guess it should be the data granularity. It is 0.5 hours, and we also have some other features all calculated. So and then we use 4 classifiers, which is random forest, key nearest neighbors, and the naive Bayesian, and the linear discrimination. So you can see that these are all classical classifiers. We also tried some deep learning methods to make the classification, but because our number of data samples are limited, so the deep learning method cannot outperform these traditional methods. So we will use the example of some traditional classifiers. So again, after we calculated the features for this new task, we will put these as the input for each classifier. And each classifier will give a score for all the candidate models. For example, the random forest will give the highest score for model number 10, and the key nearest neighbors will give the highest score for model number 7. So you can see that the different classifier will have different recommendations. So which model shall I use, or which classifier shall I trust? So the score mechanism basically combines the score of each classifier together with its confidence level. So the confidence level means how this classifier will perform average. So for example, the 50% for the random forest means, in generally speaking, the random forest has a higher classification accuracy. So we will multiply this value to this score to get a final score. So after we do this for all the classifiers, we can find out which one finally get the highest score. So we will use its recommendation. So in this case, we will use the recommendation of random forest, which is the model number 10, similar day model, to solve this forecasting problem. So based on my testing experience, so the random forest is, we can call it the best performance classifier in the classical methods. So if you ask me, hey, yeah, which classifier I should use, so I would recommend you the random forest if you want to use a traditional classification algorithm. So it's pretty reliable. So next is an example to show the scoring voting mechanism. So this is the ensemble learning results of one cluster as I showed a lot of cluster. This should be one of them. I think it should be cluster 4. So you can see that each dot still represents a forecasting problem. And if there is a circle around this dot, it means, okay, the red circle is random forest. It means the random forest gives the right recommendation for this task. So you can see that for some tasks, we do not have any circle, meaning no classifier can give the correct recommendation. But for some tasks, we have multiple circles around it, meaning this task is pretty easy to be identified, and all the forecasting, all the classifier can give the right recommendation. So this is it shows the necessary of combining different classifiers. So because you can see that different classifiers have different good areas. So this one is identified by random forest, and this one is identified by key nearest neighbors. So, so this is the accuracy level of each individual classifier and our ensemble learning classifier. So you can see that after we combining the classifiers here, we can improve its accuracy compared with any single classifier. So the baseline means if you randomly select a model as your solution among the 10 models, you will only get 10% accuracy. So that means the selection framework is effective in improving the chance to identify the actual best model. So here we use, we split the task into training and testing to see how many accuracy you can achieve. So as I mentioned, we have 46 chance to hit the best model among the 10. And you will ask that, okay, you still have a 54 chance to fail to identify the top 1 model, right? But I will tell you that it is okay because we still have a 76 chance to recommend you a top 3 model. So that means in some cases, we cannot give you the best one, but we can still give you an effective one that among the top 3 model. So it is not the best, but it still works pretty well. So because we can identify the best model or effective model for these tasks, we can reduce the overall forecasting error. So for example, the MAP is reduced and our SER ratio is also reduced. So I think you still have a question that, okay, you tell me you have a 76 chance to hit a top 3, but you still have like a 24 chance to fail to identify a top 3. So what will happen in the 24 failure cases? So next slide, we just take a closer look into the 24 failure cases. So this is a histogram of the SER ratio in the remaining 24 failure cases. So basically we have 41 cases failure among the 169 testing set. So this shows the SER ratio of the 41 cases. So you can see that although these are failure cases, meaning these models are not among the top 3, but in most cases, it still has a very small SER ratio. And this is interesting because this model is not among the top 3. So you thought it should be bad, right? But actually it is still pretty close to the ground truth. I mean, to the actual best model. So in order to understand this, we can get back to this figure. So that means for the failure cases, it mainly happens in this area. So that means in this area, although you failed to identify a top 3, but all the model performance are pretty close to each other. So in this area, so no matter which model you use, you can probably all get satisfying results. So that means our meta-learning framework mainly fails in this area. So in other words, in this area, if you fail, it's okay. it doesn't matter because all the model can solve your problem. So in this area, the model selection is not necessary. So this again proves the robustness of our model selection framework. So briefly speaking, in most cases, it can give you an effective forecasting model. But in some cases, although it cannot give you a good model, a top 3 model, but in this area, in these cases, the model recommendation is not important. So this is the stage 3, which is an example to show how this whole process goes. So firstly, you will receive a new forecasting problem. For example, please forecast the next 12 hours with 15 minutes granularity. So now you have the historical data and you need to foresee the future. So the first thing you need to do is to calculate the features for this task. So for example, its data length and its number of weather features and data granularity. And then you put these features to the trained ensemble learning classifier, and it will tell you which model you should use. And then you can use this recommendation model to solve your problem to get the forecasting results. So I think the time limit is approaching, so I will try to go faster. So here are 2 detailed examples. For example, we have 2 different tasks, task 1 and 2, and they are pretty different in all of the features. So this task 2 is probably a feeder level forecasting problem, and the task 1 is just a single user level or a transformer level forecasting problem. So I will, as I mentioned in the previous slides, we will use our trained ensemble learning classifier to give the recommendation for these 2 tasks. So for example, the similar day is recommended for the task 1, which is the actual best one. And the SRMA is the recommendation for task 2, which is the second best one. So we will use this model to solve the forecasting problem. So we get the forecasting results like this. So you can see that the forecast results follows pretty closely to the ground truth in both of the 2 cases. So this is an implementation framework. So we give this as an example to show how this framework can be implemented. So this is a cloud edge integrated framework. Basically, we have sensors like the green box, which can be considered as smart meter. It can sample data from the users. And we have edge computing devices, which is the star, so which can be used to execute the forecasting algorithm. And then we also have a cloud platform to collect the data and to train the classifier. So this framework has a few advantages. For example, the data uploading and communication is limited. And also it is pretty robust because once the cloud platform is down, we can still run a forecasting algorithm in each distribution computing device. But of course, you can implement this algorithm in a centralized way. It will also work. Okay, so this is the summary slides for today's talk. So basically, the load forecasting area is pretty well studied, and there are many existing forecasting techniques. But the problem right now is the forecasting problem in distribution system is pretty heterogeneous, so it cannot be solved by any single model. So in order to find the best model for each problem, the manual selection is pretty time consuming, so we cannot do it manually. So that's why we introduced Metalearning to automatically identify the best model for each problem so that we can improve the overall accuracy. So the characteristics of our framework is automated and scalable, meaning everything is done by the meta learner instead of human intervention. And it is scalable because you can always introduce new models or new features or new tasks to the framework without doing everything from scratch. So based on this framework, we can shorten the training time cost. We can improve the overall performance. So what I want to mention for the future direction is the automated machine learning area. The automated machine learning area is pretty interesting because our work only try to achieve the model selection automatically, but actually we can do everything automatically, including the feature extraction, including the parameter tuning. So this is a broader area which is called auto machine learning, which is also considered one of our future work. So in the end, we would like to acknowledge our sponsor because this work study is sponsored by the DOE project, and also any potential collaborations with utilities and the companies are highly welcome. So I guess next is the QA time. So any questions, please feel free to let me know. I would be glad to answer.
Thanks, Dr. Lee. I know that this was a pretty complex, methodology, including machine learning and integrating, all kinds of data sources and processes. But so how does your approach, so in general, let me back up. In general, there are lots of load forecasting models, and the problem that utilities and people who work with utilities face is how to pick the best load forecasting model for their particular situation. Yeah. This is one technique. How does your technique compare to, say, other technique or other research that's been done in this area?
This is a good question. So the first point is that currently there are a lot of load forecasting studies and implementations in utilities or companies. So the first point is that they usually use a single model, but our point is not focused on the single model, but we focus on a higher level because we believe for the utilities using a single model is not enough. So we make the model selection. So this is mainly because the flexible operation mode in the distributed system in the future. So the second point is that we have seen some similar researches already published before, but compared with our work, I think there are still some deficiencies in their work because firstly, the load forecasting problem definition is usually not very complete in their research. For example, they usually just define a few, like 10 forecasting problems or 20 forecasting problems, and then to make the model selection. So that means the testing case is not very solid. So in our case, we have over 800 cases to support our study, which all from the field measurement data. I think this is useful. And this can also be used as a standard test case in the future, we believe. And the second point is that we use the sample learning to make the model selection. So we combined a lot of different classifiers together to enhance the selection accuracy. And the next point is that we do a more extensive study in the case study part to see, okay, how many cases you can identify the best one, how many cases you cannot, but you can still get a good recommendation. So I think this makes our work more unique and solid compared with some existing works.
Okay.
Yeah.
Okay.
Yeah. I saw some questions pop up in the chat box.
Yes.
Can I just directly answer them?
Okay.
Okay. Let me check this. The first question is, and the load forecasting is a demand side response used to predict the demand power system. I was wondering if we could use any sort of forecasting to predict the supply of renewable energy plants. Yes, definitely. I think there are already a lot of forecasting techniques also exist in the supply side. For example, especially focusing on the renewable energy. So as we know, the fluctuation of renewable energy is pretty significant, such as the wind power and solar power. So accordingly, we will also have tools to solve these forecasting problems. So I think, based on my understanding, because I also worked, do some research in the PV forecasting, meaning the photovoltaic forecasting. So based on my understanding, some methods are commonly used in both the demand side and supply side. For example, the time series analysis, because the load profile and the PV or wind profile are all time series, so can use some time series methods or machine learning methods to solve them. So, but the difference is that the influencing factors for the load and the PV power or wind power is different. So, for example, the power load is mainly influenced by some weather conditions or user preferences or some economical characteristics. But the PV is mainly influenced by the irradiance, right? And the irradiance is determined by the cloud movement. So their main consideration is different. So when you do the modeling, you should pay attention to this.
But could you use your techniques just with different time series data from generation instead of load?
Yeah, that's a very good question. We haven't tested in the PV side, but I believe that some of these techniques, some of the models will work on the PV side. And for the PV side, I think model selection may also be valuable because for different weather conditions, we may need to use different forecasting models. So once you have different forecast problem, you will need probably the model selection. So this is, I think, is an interesting methodology instead of just focusing on a single model.
So if anybody's looking for a dissertation topic, there's one for you right there.
Yeah, yeah, right.
Maybe so.
Yeah, Metalearning and the automated machine learning are all very big and interesting directions.
Sure, sure. Yeah. Could you look at one of the other questions and
sure.
Answer one of those?
So the next one is how long historical data is used to train the engine? So I believe when you talk about historical data, you are talking about the base learning layer, meaning we have 10 models, you will need to use historical data to train the model, 10 model. So here, I think the answer is it is different for different tasks. So so here since we have over 800 forecasting tasks, and each of them has different historical data. So meaning, for example, for some tasks we have 1 month historical data, and some for 6 months, and some for 1 year. So the historical data length is different for different tasks. So so based on my experience, for example, for the SREMA model, support vector regression and similar day model, it do not require too much historical data to be trained because it's not deep learning model. It do not require too much data. But for the LSTM model, it requires much more data than the others because it has much more parameters. So this is also an important feature to make the model selection. So you can see from the results that if you only have 1 month's data, the ensemble learning classifier will not suggest you to use LSTM because you cannot well train it based on 1 month's data. So it will mainly give you like SREMA or similar day. So this is probably the answer to your question. So it varies for different tasks. And the next question is, can this tool also calculate the error in the best forecasting model? Yes, because once you select the best model and you use the model to solve your forecasting problem, you can still, of course, test the performance of the best model to get these errors. Yes, I think. Next is, Have you tried your methods for longer term forecasting, for example, 10 years? Can you comment about? Okay, I think this is a very good question. So currently, you can see that we mainly focus on the short-term or mid-term forecasting problem because the whole framework is mainly used to support the distribution system operation. Because in the distribution system operation, it's pretty flexible and you will always facing some new forecasting problems that you have never seen before. Because, for example, hey, this is this is a new formulated microgrid, and you haven't seen it before, but you need to get the forecasting immediately right now. So you will need to use this framework to give the recommendation. But for the planning problem, I think you can still use this methodology, but it's do not have equal value as the operation problem, because the planning problem is a long-term problem, and you have plenty of time to make your model selection manually even. So because it do not require you to make real-time decisions, so you may not require that much for such a framework. But certainly you can use it to have a try. We haven't tried it yet. So next question is, how do you get this much data set? What is maximum load forecast time step you have chosen for? The data set is, we have some collaborations with Wilson Energy, which is a local utility. So they will provide us some data, smart meter level data, and some, so we can use this data to set up different tasks. And we also have some purchased the Pecan Street data set, which also include over 1,000 smart meter data with 1 minute granularity. So based on the real smart meter data, we can create different forecasting tasks.
So Dr. Lee, Wilson Energy is here in North Carolina?
Yeah, I think so.
Okay, yeah, I think through the town of Wilson, and then Pecan Street is in Austin, Texas.
Yeah, right.
But they have, they have made their data, like you said, available.
Yeah, exactly.
For purchase.
Yeah,
and it's an entire neighborhood of, residential buildings that have solar.
Yeah, exactly.
Batteries in it. Yeah.
Yeah. Well, thanks for the clarification.
Yeah. Tell you what, I'm looking at our time, and we are right here at the top of the hour. I know we have just a few more questions that people have put in the chat. So, Dr. Lee, I don't know if it's possible if you could, copy those real quick before we end the webinar, and maybe, I don't know. Here's what I'm actually going to suggest. For those of you who asked those questions, please send Dr. Lee an email directly, and hopefully he'll be able to answer those.
Yeah, sure, no problem.
If you could go to your contact information again one more time.
Yeah, sorry, I should go the talk quicker so we
no, that's okay. It's all of our webinars have been like this. The topics are very interesting. The lots of questions from the audience. So I do want to say thank you again to everyone who joined us. As we mentioned earlier, this webinar was recorded, and so it will be available on the Department of Electrical and Computer Engineering YouTube page from NC State University. And so you can view that later at your leisure. So thank you again, everyone, but we're going to end our webinar for today. Dr. Lee, thanks a lot.
Yes, thank you.